Then let us begin. So we talked about line integrals, and we saw that when we deal a line integral of a conservative function, it's actually really nice. So it's like, hey, line integrals can be easy if what we're working with is a conservative thing. And the moral is that we said, the conservative functions are essentially functions which are like a derivative. So we were able to relate the derivative along the line to what's happening with the potential function at the endpoint. So somehow there's a relationship between a derivative on the inside with the function on the boundary. And one of the things that we saw about this is because I only care about the endpoints, if my endpoints match, which is to say that I'm a closed curve, so closed curve means that the endpoints match, then my starting point and my ending points are the same. So I get 0. Now we're going to deal with a lot of integrals where the endpoints match, so we want to come up with special notation to indicate this. So you'll see we put a little bit of a circle there. So when you see that, you should think, okay, this is a curve that's closed. So it's a closed curve. Now, conservative functions, integral will be easy. And the question is, well, what happens if our function is not conservative? Is there anything that can be done? And the answer is today's discussion. It's called Green's theorem. So here you go. Green's theorem says the following. Suppose you have a region, and right now we're going to be in the xy plane. So I'm in the xy plane. And my curve is the boundary of the region. Now, you might say that symbol here that we're using looks an awful lot like the same symbol we used when we talked about partial derivatives. And it is. See, mathematicians, we're environmentally conscious. We like to recycle our symbols. So just keep in mind, if you see that symbol, know the context. So if you see that in relationship to some sort of a shape, be it in the plane or maybe in 3 dimensions, we're talking about the boundary. So here, this is the boundary of the region. So my region here, the curve is the boundary. But we now also need to talk about orientation, because orientation matters. In fact, a lot of calculus has orientation built into it, but oftentimes we sort of put it into the background and don't think about it. So we need to orient the curve in some direction. So now we have to figure out, well, what's the right direction? Well, there's a convention. And what's the convention? Well, it's the following. Imagine you're standing on the plane. So to help me demonstrate this, I've brought an associate. This is a brainy Smurf. Now you can tell brainy Smurf is a smart person because they wear glasses. All right. So what's the rule? You stand on the plane, and the rule is that as you travel along the direction of the curve, your region should be on your left-hand side. So that's the rule. Don't try to remember counterclockwise. Don't try to remember clockwise. Just remember it should be on your left-hand side. And that's the orientation. Now, you might say, wait a second. If the curve is oriented, what does it mean to be? What does it mean to say that the region is oriented? There's no orientation for the region, but actually, there kind of is an orientation for the region because you'll remember our associate is standing on the plane. Well, brainy Smurf could have been standing underneath the plane. There was a choice that was made, and that's the orientation. Now, you might say, okay, but how do I remember that I should have it on the left-hand side? Is there some easy way to remember it? And there is. You just think of the song. The great mathematician Beyonce. To the left, when you walk the curve, keep the region to your left. So, you didn't realize, you thought you were signing up for Calculus 3, multivariable calculus. No, this is Calculus 3, the musical. So, but that's, just remember, on your left-hand side. Okay, so that's the setup. We have our region, it has a bounding curve, and it's been oriented correctly. The conclusion is that when we're integrating on the boundary, so m dx plus n dy, it's equal to the integral over the region of partial n partial x minus partial n partial y. Now, we'll get into sort of why that's true a little bit. We'll touch on it. But for now, let's just say, okay, that's the result. All right. Let's go back to our sort of theme. Our theme here is to say there's something about knowing what's happening with the derivative on the interior and knowing what's happening with the original function on the boundary. We said that for line integrals. It's still true. Because think about it. The integral over the interior region, it's partial derivatives. So partial n partial x minus partial n partial y. So this part is like, it's acting like a derivative, and that's on the inside, whereas here I'm on the boundary, and it's essentially the original function. So you're going to see this theme several more times before the semester is done. Okay, let's do a quick sketch of the proof. Now, here we go. We're going to assume our shape is very, very simple, and we're also going to do our function is very, very simple, but it doesn't take much more than what we talk about to really go all the way. So suppose I have my region here. So this is my region. I'll call it R, just to emphasize. So my curve here is a combination of two curves. I have a curve on the top and a curve on the bottom. And I've split them such that I'm going between two locations. So in particular, I'm thinking on here, I'm at x equals a, and on this other side, I'm at x equals b. So I'm going between a and b, and I can parameterize the curves very simply. So on the bottom curve, let's start with that one. That's easier to see. I have some curve y equals f of x, and I go from a to b. So the parameterization is very simple. X, f of x, from a to b. Now the top, well, that's some other curve. Y equals g of x. And I'm also going from a to b, but here's the part where you have to be careful. If I went from a to b, I would be going opposite the orientation. Well, that's okay. I'll just say that minus c1. So if I change the direction, I just change the result. So I can talk about orienting the curve. I can just put a minus in front of it. It means I travel the curve backwards. So minus c1 would be if I traveled it the wrong way. So what's the special case? Well, I'm going to integrate m dx on the outside curve. Well, the curve has two pieces. So I'm going to have c1 plus c2. All right, well, that's not so bad. That's pretty straightforward. And now we say, hey, we have parameterizations here. So we do the parameterizations. You'll notice because c1 went the wrong direction, that's why there's a minus sign. So we now can write our integral in the following way. So minus integral a to b mx g of x dx, and plus integral a to b mx f of x dx. Now, here's sort of the great, wow, that's kind of a neat idea moment, which is let's put them into one integral as the integral from a to b m of xy, but where I evaluate y equals f of x to y equals g of x. And if you think about what happens here, we're saying, look, plug in, wherever you see y, plug in g of x. You'd get mx g of x, that term. And then you subtract, plug in f of x. Well, mx f of x. But I subtract that, there's another minus, so I get that term. And now, if you write it in this way, we say, that looks an awful lot like we just did an integral and we evaluated. Well, which integral? Well, it has to be something where we integrated, we want it to be the y, so probably it's the second entry, and if we think about it, it's not very hard. The answer is the derivative of the function in the second entry, partial n partial y, xy. So this is the fundamental theorem of calculus. So Green's theorem, this step right there, this is the fundamental theorem of calculus that allows us to do that. That says if I want to integrate a derivative, I just have the original function evaluated at the endpoints. So not only is Green's theorem like the fundamental theorem of calculus, it is the fundamental theorem of calculus, just spruced up a little bit. And finally, the last thing to note, well, this is minus partial n partial y, and what's the bounds? Well, I'm going x from a to b, and y goes from f of x to g of x, which means I'm over my region. So we've basically proven that special case. The other one is very similar. It's a similar type argument, just turned on the side. All right, let's try this out. So some examples. Let C be the oriented curve that goes from 0, 0 to 2, 2 to 0, 2 and back to 0, 0. And we're going to find the integral along this curve, 3x squared y dx plus x plus arctangent y squared dy. Well, let's see what our region looks like to begin with. Actually, there's no region. This is a curve. Why did I say the word region? I wonder. We start at 0, 0. Then we're going to go to 2, 2. So here's 2, 2. Then we're going to go to 0, 2. So there's 0, 2. And then we're going to go back. So we're going, our curve has 3 parts. And we want to find the integral along this curve of 3x squared y dx plus x plus arctangent y squared dy. Now, one way we could do this is to actually do the integrals. I'd do 3 of them because there's 3 parts. And I'd work my way through, and I'd be annoyed because I'd have a hard time doing that arctangent of y squared. As much as I love arctangent, it doesn't always love me back. So, a better idea is to think about the theory. So, in particular, we say, well, what do? I have a curve C. So I already have my curve C. What I can do is I can say, well, that curve, I can treat it as though it was a bounding curve. So even though I wasn't given a region, I can say, once I have a closed curve, I just fill it in. So let's fill in our region. If we fill it in, what we see is we get something fairly simple. We get a nice triangle. So our region is going to be this triangular shape. And now we can say that our integral, and of course we check if it's oriented correctly. Now what would happen if it wasn't oriented correctly? So right now, is it oriented correctly? Yes, because it's to the left. Okay, what would happen if it wasn't oriented correctly? What would be the result? Yeah, you just flip it. To flip the orientation means put a negative in. So it's easy to correct the wrong orientation by changing the sign. That's where signs come from in essence. It's the orientation. All right, so we can say that this integral is the integral over our whole region of something. Well, let's look at the pieces. There's my m dx. There's my n dy. So we're going to take partial n partial x. Partial n partial x will give us 1. And then we're going to subtract partial m partial y. So we subtract 3x squared. So here, what you'll see is we can have problems set up that look terrible because of that arctangent part, but lo and behold, that part will vanish if we try and go and apply the theory. Now, you might say, that was highly suspicious. Why did that happen? Well, we planned it for that way. But another way to think about it is if you think back to the theory, we're like, well, there's a derivative on the inside, there's a function on the outside. In some sense, we were saying, well, we're just going to choose some constants that are really messy looking. So we can find ways to make you nervous. Don't be distracted. All right, I already can tell I made a mistake here because I should have used a green color. It's Green's theorem. Oh well, that's okay. You don't have to use a green color. It's all right. It still works. So let's finish this up. Now, here, it's a simple triangular region, nothing complicated. Should we integrate this dy dx or dx dy? And the answer, of course, is both are okay. Probably, I would be biased to say let's slice horizontally. Now, the reason I'd be tempted to say let's slice horizontally is because the bounding curve over here is a very nice bounding curve. It's x equals 0. And anytime you can get 0 as one of your bounding curves, that's a really good situation. this bounding curve from 0, 0 to 2, 2 is x equals y, and the top one we can write as y equals 2. So if we were to slice horizontally, which means that we were going to integrate this in the order dx dy, we would say, well, where does y go from? 0 to 2. Where does x go from? 0 to y, because I'm going from 0 to y. So 0 to 2, integrate this with respect to x. We're going to get x minus x cubed, evaluated from 0 to y, dy. So this would become integral 0 to 2 of y minus y cubed dy. So that becomes the integral from 0 to 2. Oh, no, we'll just integrate. 1/2 y squared minus 1/4 y to the 4th. Evaluate that from 0 to 2. And 0 goes to 0. 2 squared is 4 times 1/2 is 2. 2 to the 4th is 16 times the 4th is 4. 2 minus 4, negative 2. That's what it looks like, negative 2. Now, is it okay to get a negative answer? Yeah, it's okay. It's all right. Integrals are totals, and totals can be negative. All right, let's do something else. So one of the things about Green's theorem, which makes it nice, is it has an application to it. So there's this tool that exists, or, well, it did exist back before technology came in, called the planimeter. You can look it up. These are actual tools. And what is a planimeter? Well, it looked something along the lines of the following. You'd have a little stand here, and attached to that, you'd have a little arm that you could extend out, and it might bend in several places, and then there'd be a little tip that would go down. And what you would be doing here is you'd be taking this planimeter, and you would take the tip, and you'd put it on the curve of some shape, and you would trace out that curve. And you would trace it, so you went all the way around the curve until you got back to the beginning. And then once you got back to the beginning, lo and behold, there'd be a readout on the machine. And the readout was the amount of area that was inside your region. So somehow this machine was able to say, I can figure out how much area you have if you tell me about the boundary. And how was it doing it? The answer was, it was doing a line integral. It was a mechanical device that was set up to do a line integration. It, in particular, was essentially doing this line integral. It was integrating along the curve. It knew where your current position was, and it knew how much you were changing in the other direction. So in other words, it knew x and it knew how the y was changing. Well, if you apply Green's theorem to that integral, what do we get? Well, we get the x dy. So that's n dy. So partial m partial y is 0, and partial n partial x is 1. So you get 1 minus 0 dA. And if you integrate 1, it's the area of your region. So this is a nice way to show that, calculus, it has applications. And, of course, modern technology, you use a computer, and the computer does it automatically. But back in the old days, calculus was good. Still good. It's still good. So we can do this to find the area of a region bounded by a curve. And here's an example. Suppose I have the following curve. C is a cosine t, b sine t. And t goes between 0 and 2 pi. Now, before we start, does anybody recognize what that looks like? A cosine t, b sine t? It's a lot like a circle. That's certainly not hard to see. If you cut up the a and b, you'd see cosine sine, which is a circle. Some people were saying oval. Someone said ellipse, and it actually is. This is an ellipse. So what it is you go out A in the x direction, and you go out B in the y direction. And you form that ellipse. So an ellipse is essentially a circle, but where you've stretched it by different amounts in two directions. So in one direction, I took my circle and I stretched it by A. The other direction, I stretched it by B. So the question is, how much area is in this ellipse? Does anybody know the formula for the area of an ellipse off the top of their head? You're about to. You're about to. Okay, well, let's do it. So here's the thing. Now this uses Green's theorem kind of in reverse, because it says we're after the area, which is the integral over our region of 1. And we say instead of integrating over our region, we integrate over the boundary. So we're going to integrate on the boundary of our curve x dy. So we've transformed our finding our area into doing a line integral. So how do line integrals work? Well, they work the same thing we've done all our line integrals. So this will be an integral. We turn everything into t. So what are the bounds? 0 to 2 pi. What does x become? A cosine t. And what does dy become? B cosine t. And then there's a dt. Now, so we can factor out, this is a, b, those are constants, so they can come out of the integral, 0 to 2 pi of cosine squared. Well, what's the right way to integrate cosine squared? Power reduction. Do you remember it? We learned it once. There's a half and plus a half. So the cosine squared is the plus a half. The cosine squared is the minus a half. Cosine squared 2t. So this is, maybe we can squeeze it in, AB. Well, the integral of a half, that's not bad. That's a half t. What's the integral of 1/2 cosine 2t? 1/4 of sine 2t. And we're going to evaluate from 0 to 2 pi. We'll put the answer over here. So we plug in 2 pi. A half times 2 pi is pi. Okay, then we have still the AB. So we have a, b, pi. Sine of 4 pi. 0. Okay, plug in 0. Half times 0, 0. Sine of 0, 0. So, that's it. So the area of an ellipse is actually really a beautiful formula. You take whatever this distance is, we can call it the minor axis or major axis or axis number 1, and then you have the other axis, and whatever the lengths are, you multiply those together, and then times pi. Cool. Now, one way to check the formula is think about a circle. Circle would have a and b both equal to r, so you'd end up with pi r squared. All right. So that's all well and good, but what happens if our region isn't quite so simple? In particular, what if our region was a little bit holy? In other words, it had holes in it. So a holy region. Well, the answer is it still works. But you have to be careful. So what do I mean by be careful? You got to use the entire boundary. And the other thing is you have to make sure that the boundary is oriented correctly. So that is to say, you always keep the region to your left-hand side. That's why I don't like to use the terms counterclockwise or clockwise, because once you start putting holes in things, it doesn't work. So if you check, you'll see here on the outside, it's running what we would call counterclockwise, but on the inside, it runs clockwise. But in both cases, you can imagine just a little person standing on the edge, and if they were walking along in the arrow, on the outside, the region is to their left. But if you went onto one of these inner parts, and this person walked along in the direction of the arrow, then the inside is to the left. So there's a consistency there. Now, you might wonder, how do you prove things with holes, or how does it work? And the answer is actually quite simple. What we do is we cut. We put a little tiny slice. It's like we pull out a pair of scissors so what does that do? Well, what it does is it really says there's no more holes, because follow the boundary along. So So as I follow the curve, I come to the cut, then I go down, and then I come around, and I go back up. And then I keep following the boundary till I come to the cut, go around, back down, and lo and behold, it's now a single curve. By adding these slices in, there's no more holes. Now you might disagree with me because you might say, that looks kind of like a hole, Steve. But it's not. It's not a hole in the following sense. Up here when I talk about a hole, I say, look, I can circle around it and I have none of my bounding curve. But down here, lo and behold, because of this cut, you'll see no matter how I try to circle the hole, I'm going to have to intersect my bounding curve. So it's not a hole in my region anymore. So that's what I mean. Now you might also object by saying, hold on, you've added stuff to your curve. Won't that change your answer? Well, does it change our answer? And why not? All right. It will not change our answer. The reason it won't change our answer is, notice, how many times do you walk along the cut? So if I come in, I'm going to walk once along the cut, then I'm going to walk a second time along the cut to get out. So I travel along the cut twice. You're saying, Steve, you just made the problem twice as bad. But what about the directions? Opposite directions. When you travel something in an opposite direction, what changes to the value? You flip the sign, and so traveling in the opposite directions, they cancel each other out. So you get 0. Perfect. Perfect. Oops. When I did this in class, I made a mistake. So it's easy to make mistakes. Fortunately, I can redo it. And what's the lesson? Well, be careful and check your work. So let's see what we have here. C1 is a circle centered at the origin of radius 1 oriented clockwise. Now notice the orientation here is really emphasized to say, it's oriented clockwise. So radius 1 circle, and we go in the direction of a clock. So we're going that way. All right. And C2, it's a circle centered at the origin of radius 2. And now that circle is oriented counterclockwise. So here we go. That circle oriented counterclockwise. So what is C? Well, C, whoops, not marked. There we go. C is a combination of the two. So oftentimes we've already thought about this idea of saying, we can split curves into pieces, and we can do each piece. In this case, the pieces aren't connected, but that's okay. Still the same philosophy. All right. Well, what are we going to do? How are we going to solve this problem? The answer won't surprise you, because what we do is do what we've been doing. We say, well, let's think of these curves, or the set of curves, as the boundary of some region in the plane. In our case, this boundary would be almost like a flat donut. Now, if we wanted to sound fancy, we can say the word annulus, which is the fancy way of saying flat donut. All right. And you stare at this and say, okay, is the orientation consistent? In other words, is the orientation correct? So that means is the region always to our left? To our left, to our left? And the answer is yes. So as I walk along the outside, the region's on this side. So it's to the left. So as we say, when we say to the left, it's like follow the curve. If you turn to the left, you're going to walk in. On the inner curve, as we walk along, if we turn to our left, we're going to go, again, into our region. So into it. All right, so this is the right orientation. So we're going to call this R. So if we call this N, then applying Green's theorem, this is the integral over our region of n sub x minus m sub y dA. So that's going to be the integral over our region. Come here. Now it looks terrible, but remember we're taking derivative with respect to x. So this log sine squared y plus 1 is gone. It becomes just simply 1 minus m sub y. Well, the e to the x to the 7th, gone. 3x squared y, well, that's 3x squared. Put some parentheses here. And derivative of y cubed, 3y squared. So, we get n sub x, 1, minus m sub y, 3x squared plus 3y squared. Now this problem is practically screaming out to use polar. Because, well, two things. First off, notice the function. You can write it as 3 times x squared plus y squared. That's very clean in polar coordinates. But even more is the region. We have things which are between two circles. So when you see the bounding curves as being circles, it's highly suggestive that perhaps polar coordinates would be a better thing to use. So let's go to polar. So it's going to be an integral. We switch our function to polar. 1 minus 3, and x squared plus y squared becomes r squared. The dA becomes r dr d theta. Theta, we go all the way around, so 0 to 2 pi. And r, well, we come out from the center. So we're going to go start at 1, go to 2. 1 to 2. Now, this integral, it's a nice kind of integral. Notice, in particular, our bounds are constants, and so we can pull it apart. So this becomes integral 0 to 2 pi of d theta. Well, that's a nice integral. And integral 1 to 2 of the rest. Now here, anticipating what's going to happen, we're going to distribute the r. So r minus 3r cubed dr. All right. Well, the first integral is 2 pi. The second integral, a little bit more work. That's going to be 1/2 r squared minus 3/4 r cubed. And we're going to evaluate 1 to 2. So just this part here, we put it in 2. 1/2 times 2 squared, it's 1/2 times 4, which is 2. Well, 2 cubed, 8. All right, times 3/4. So, 8 times 3/4. Well, Oh, whoops. Haha. That's not 8. It's supposed to be 4. Add 1. Good. 16 times 3/4. 12. There we go. 2 minus 12. All right. And then we're going to subtract 1/2 minus 3/4. Well, common denominator is 4. So this is going to become 8 minus, then 48 minus 2/4, and plus 3/4. All right. So we get 8 minus 48. Well, that's negative 40. And then we have minus 2 plus 3. Well, that's plus 1. Negative 40 plus 1 would give us negative 39/4. Now, what's our final answer? You have to multiply these two terms together. So our final answer, 2 pi times negative 39/4. Well, you can't have a 2 go into the 4. So we're going to end up with negative 39/2 pi. There we go. And that's it. That's the answer. All right. Well, let's get back to it. I want to talk about two special cases, or rather maybe I should say another way to think about what's happening here. And we're going to try to connect these to what we're going to do with the rest of the semester. So the first special case is to think about, we're doing a line integral, but we're going to have the unit tangent vector. So remember, unit tangent vectors is we're coming through at each point and we're drawing what we call the direction. All right, so these are our unit tangent vectors. So as you move around the curve, they swing around. And we're going to look at a line integral, so we have the following. So our unit tangent vectors, you can write that as dx, ds, dy, ds. So the ds, recall, is just a distance of length as you move along the curve. So change in x as you move along a small bit of length. So we can look at the following. The integral along the curve of f dot t ds, which means we have a picture somewhat akin to the following picture. So over here, these little arrows here, that's the f. It's a vector field. And so we can say, well, look at the vector field. What's happening when I'm multiplying the dot product, f dot t? What is it measuring? How do I find that? Well, so f dot t ds, that's mn, that's my function f. TDS is what I have up above. Nothing too surprising, which is really just the integral along the curve of m dx plus m dy, which is what? Well, that's Green's theorem. It's the integral over our region, partial n partial x minus partial n partial y. Now, for this picture, it's not so clear what to see. I mean, in some senses, you can take a look, and there are points where if you look at the value of your vector field and the unit tangent, they're almost perpendicular, which means it's 0. There's other points where they're almost in the same direction. It's not so clear what information we're gleaning. But earlier this week, I said there will come a moment when I say, does this look familiar? This is that moment. Does this look familiar? Partial n partial x minus partial n partial y. Did we see anything like that before? We did. Do you remember where? You have to, what? Curl. The curl. That was that last slot of the curl. So another way to remember which one it is, just say, what should that third entry of the curl be? So this is like a curl, but of course it can't really be a curl because you can't do a curl of a two-dimensional vector. But how do we turn it into a three-dimensional vector? Add 0 on the end. So if you take the curl of mn0 and grab the third part, that is partial n partial x minus partial n partial y. So we have that the integral along the curve of f dot t ds is the integral over the region of the curl mn0 dot k. So dot k is just saying grab that third entry in the curl. Now, after the next exam, we're going to see that this is going to be generalized to something called Stokes' theorem. This is a very special case. So we are going to talk about that. But again, that's after the third exam. You don't need to know it now. But we're going to take this idea and say, let's move up into the next dimension. There's a second thing to do, which is talk about the outward normal vectors. So here, what's the direction? Well, the unit tangents point with direction of motion. The outward normals are going to point perpendicular to motion. So they point out here. Now, in some sense, there's a question, how do you know how to find the outward normals? Because it's not so clear how to find it. In some sense, we're saying, oh, the unit tangents are x prime, y prime. More or less, that's what they are. But there's a choice to make. You'll notice there's a key word, outward. Because you could also, of course, have something pointing inward. So it turns out that if you want to have outward, once you understand the orientation, it's actually built in. So it's going to be dy minus dx. Now, sort of a sanity check, these should be perpendicular. Because one is with motion, one is perpendicular. And if you multiply, you'll get dx dy minus dy dx. So you get 0, so that's good. They are perpendicular. It's easy to see that they both have the same length. Now, why did we pick the convention? Well, you should try to convince yourself that it works. So let's just look up here. So if I'm moving along the curve, what's true about my y right now? Is it changing much? No. It's very small change. What's true about x? It's changing, but how is it changing? So if I'm moving here from right to left, what can you tell me about the sign of x? The sign of the change. It's negative. I'm going down. So if we think about it, our change in y didn't change very much at all. So the vector will have a very small change in the x direction. Then, on the other hand, the change in x, that was significant change, but it was negative. Minus a negative means it'll be a positive, so it will point up. So it is consistent with the picture. Now, the good news is we don't have to know that, and we just say, let's just apply it. So we apply the integral, mn dot dy ds minus dx ds, and we get down to this point, minus n dx plus m dy. And the question is, how do we attack that integral? What tool do we use? We use Green's theorem. Now you might say, wait a second, hold on. Green's theorem says you need an m and an n. No, Green's theorem it's a placeholder symbol. Whatever's in front of the dy term, okay, so in this case it's the m, take the derivative of that with respect to x. Whatever's in front of the dx term, take the derivative of that with respect to y. So, if you follow it through, what do we get? Well, we're going to get partial m partial x subtract the negative of partial n partial y. Or, if you like, that's m sub x plus n sub y. Now, have we seen anything that looks like m sub x plus n sub y? Here, we'll make this a plus. What? Anything? Anything? Divergence. It's the divergence of your vector field. So, we get the following. So, if I want to know what's happening on the boundary, I can look at the divergence. Now, this is kind of like the divergence theorem. This is the other big idea that's coming up after the exam. We're going to take this idea and shoot it up to 3 dimensions. Now, one of the things that you can look at is you can say, well, what's being measured here? So, if you look at your picture, you can see that for this particular vector field, that in many cases, our outward pointing normals actually kind of match with the particular vector field we have here. Now, that's kind of a coincidence, but the question is, what is that saying? It's saying that, in our case, we're going to get positive values, because f and n are parallel to each other. F dot n are going to be positive. Well, how do we interpret it? So the answer is we're going to think of these things as being measuring a flow. So in particular, think of our vector field as modeling a fluid flow or electrical flow. It's flow. And what I want to know is how much flow is passing through the surface. Well, to figure that out, at every point I look at this amount, f dot n. That's the rate of flow at a particular point, and the length gives us the amount of flow at a particular point, and we add it up. So the conclusion is that our flow through the boundary is found by integrating the divergence over the region. So we can compute flow in 2 ways. Now, vaguely speaking, we talked about the divergence as saying it measures something, and the answer is, what is it trying to measure? It's trying to measure how much compression you have or how much expansion you have. So we get the following problem. So the flux is found by integrating along the curve f dot n, but it's equivalent under Green's theorem integrating the divergence. So, example. Let C be the curve that starts at 2, 0. So let's see if we can draw this picture. So we're starting at 2, 0. And then we're going to go on the top half of the circle of radius 2, centered at 0, 0, until we get to negative 2, 0. So it's the top half of the circle. So we come along to here. So here's our curve, C. And then we're not done yet. Then it goes on the top half of a circle of radius 1, centered at minus 1, 0 to 0, 0. Okay, so if we're centered at negative 1, we're going to come along here. So there's our second part. And then we finally go on the top half of the circle centered at 1, 0 to 2, 0. So the top half again. So there's our second part of our curve. So our curve has this shape here. So the question is, let's find the flow across our curve for this particular value f. Well, based on what we saw, if I want to compute the flow, that means I'm going to integrate on the curve f dot n ds. But almost always in problems like this, we ask, is there a better way? And hopefully by now, you probably are thinking, what if we made that curve the boundary of a region? That's a good idea. So we'll do that. As with all good ideas, they deserve to be done. All right, so there's our region. So according to this is going to be the integral over our region, the divergence of our vector field. Well, what's the divergence? Take the derivative of the first term with respect to x, because remember, this is the m, this is your n, and we want m sub x plus n sub y. That's our divergence. So derivative of the first entry with respect to x gives us y squared over 1 plus y squared, which at this point we're like, oh man, we got to integrate that? Well, maybe things are going to look up when we come here. Now go to the second term. Take the derivative with respect to respect to y. Okay, derivative of y sine x cubed with respect to y. Sine x cubed is like, oh man. Oh. Okay, derivative of arctangent y. 1 over 1 plus y squared. All right. Now at this point, you might be getting nervous and saying, this doesn't feel like a 1 minute problem from here. Well, but now we start looking for things. Does anything pop out to us? What? You can certainly add the last and the first together, and if we add those together, what do you get? 1. Yeah. So this is the integral of our region of 1 dA. We'll handle that one in a second. Plus, there's another piece, sine of x cubed dA. Now, one of these is easy, and the other one is also easy. Which one do you want to do first, the easy one or the easy one? Okay, good choice. All right, let's do the integral of 1. Well, it's the area. So what do? It's the area of a half circle of radius 2. Well, a circle of radius 2 has how much area? 4 pi. So half of the circle, so in other words, the top half of the circle would be 2 pi, but then I subtract out a whole circle of 1, because there's a half circle of 1, half circle of 1, and a circle of 1 would have area 1, which means that the integral of this region of 1 is pi. So this is pi. All right, so you're probably thinking, that one doesn't look easy. Because that function is a very unusual function. A strange, peculiar, weird. Some people might even say, odd. This is an odd function. Now, what's important about the odd function is you see there's symmetry if I flip across the axis here. So whatever the value is over here on one side, it's exactly the opposite value on the other side. Which means that whatever the value is on the right-hand side will cancel with the left-hand side. So what's this integral? It's 0 by symmetry. So the answer is pi. All right. To be continued. Okay, one last example. And this one's kind of an interesting example. So let's do it. Let C be the curve which consists of straight line segments where you go between some points. So we're going to start off way down in the corner at 0, 0, to go to 2, 1, go to 4, 0, go to 5, 2, then we're going to go to 4, 4, over to 2, 3, 0, 4, minus 1, 2, and back to 0, 0. Now the key thing here is to notice, first off, it is oriented, and it's also close. So we get back to where we started. And now, for this curve, we want to find the integral on this curve of y squared plus cosine of x cubed minus xy dx plus 2xy plus 1 over 1 plus e to the 2y dy. Well, at this point, not a big surprise what's going to happen next. What's going to happen? We're going to try to pull out our tool. And our tool says, look, this is a curve, but it's not just a curve. I can say this curve bounds something, and it bounds a region. So we're going to fill in the region. So we fill in our region, and we say, aha, now that we have our region filled in, we can now think of it in a slightly better way. In particular, we're going to think about using our tool, Green's theorem. So here's our region R. According to Green's theorem, this will be the integral over our region of n sub x. So come here, take the derivative of this term with respect to x. Well, we'll get 2y and then 0, because there's no x there. All right, subtract. Now come to our next term. This is our m. And we're going to take the derivative of this with respect to y. So y squared, derivative of y squared with respect to y, 2y. Derivative of cosine of x cubed, derivative of that with respect to y, 0, gone. Minus xy, derivative of that with respect to y is minus x. And write that dA. Now we see, aha, we are in luck. The two y's cancel. And we have a minus minus, making it plus. So the only thing we have to do is say, look, this is the integral over our region of x dA. Now, not so bad, except we actually have to do that integral. And, well, do we? Can we think of a different way to think about this problem? So what do we have? We have the integral of x dA. And so when we look at this problem, it's good to sort of take a moment and think about, have we seen any integral like that before? Something that looks like the integral of x dA. All right, take a moment. Maybe one more moment. Do you see it? The answer is we have seen an integral which has an x dA. So where is that integral shown up? Well, when you look at the moment with respect to the y-axis, that's equal to the integral over your region of x times your density, so distance times density, dA. Well, let's just make density equal to 1. And now what we can say is, aha, our moment is with respect to y, it's the integral over our region of x dA. And so we're now like, aha, we've turned our problem into something else, or at least given it a different name. But is it a useful name? Well, what is this finding? Well, it's finding the moment. What do we do with the moment? Well, one thing we can do with the moment is we can say that the center of mass, x by y bar, x bar, y bar, well, what is that? That's the moment with respect to the y-axis divided by the mass, and the moment with respect to the x-axis divided by the mass. Now, in essence, we're looking for just that piece. But do we know anything? And if we think about it, we say, well, look, we're treating our region like it's constant density. So look at our region here. Constant density, is there any symmetry? I think there is. In fact, there's a lot of symmetry here. For instance, on this line, we see that the shape is symmetric across that line. But we also see on that line, the shape is symmetric across that line, which means that if we're thinking of this as a region with constant density, then the center of mass is at the point 2, 2. All right, well, that's not something, it's something. But what do we do with that information? So we can now say the following. We can say that the integral over our region of x dA, which is our my, if we think of our region as constant density and we're finding the moment, well, that's now going to be equal to, if we look at this part, 2 times what the mass is. So that's 2 times the integral over our region of dA. In other words, it's twice the area. So, what do we need to do? The answer is we have to count area. Well, we can count area. Actually, we can count area pretty clean, because look at what we can do. We've got lots of squares. So for each one of these squares, that's going to be an area of 1. All right. So we got 1, 2, 3, 4, 5, 6, 7, 8. But look at the triangles. For each triangle, it has 2 and 1, so 1/2 base height. Each one of these triangles is also an area of 1. So now if we go through and count the triangles as well, let's see what we're going to be up to. And, well, I'll start here. 9, 10, 11, 12, 13, 14, 15, 16. So the area of this shape is 16. Now put it here. So our final answer is 2 times 16, which is 32. All right, well, that's pretty clean. Now, you might say, are we allowed to do this? In other words, when we started this problem, we were looking for a line integral. What allows us to say, let's think about this in terms of a moment? And the answer is, you're allowed to interpret any integral that's convenient for interpretation. Now, when you're doing an integral problem, in some sense you can say, look, it's an integral problem. It exists abstractly, and I can do it mathematically. But really, you should say integrals represent things, and oftentimes the same integral can represent multiple things. So if we reached a certain point in the computation and say it would be really convenient for us to reinterpret what this integral is, then we take that moment, reinterpret it, and we have an advantage. And in this case, it worked out very nicely. Now, are there other ways to do it? Absolutely. And you'll get the same answer. But sometimes it pays to take a second, pause, and think about where you're at. And ask yourself, I wonder if there's a better way. Because sometimes there is. All right.